The Story of Everything, Chapter 4, the first 100 billionth of a second, the Electroweak Epoch, 10 to the negative 35 to 10 to the negative 11 seconds. We have arrived at 10 to the negative 35 seconds after the Big Bang, my butterfly tour guide announced, when the outrageous expansion of the inflation epoch suddenly ended. During inflation, the universe doubled in size every 10 to the negative 38 seconds, so it is now at least 10 to the 78 times larger than it was at the beginning of inflation, meaning the entire universe is now at least as large as the 21st century observable universe. But it's not the 21st century now, so the part of the universe that is observable in the 21st century is currently only just big enough for you to fit in. I'm pausing it here. And there she paused it. In reality, the universe still would have looked pitch black to human eyes at the end of inflation. But Sophia was continuing to let me see things for the sake of the lesson. What I now saw was similar to the seething sea of sizzling particles slamming into each other I had seen before inflation. The universe was still black underneath it all, but this time there were far more colors, dozens of them. Looking close with the magic microvision Sophia gave me, which I needed now that I was my normal human size, there were again pairs of lights either diverging or colliding in a bright flash. Others looked like they were in the process of ricocheting off everything else in a blur of lines and whirls, and now I saw faint gray streaks of particles. When I looked at the whole picture, it all looked like TV static frozen in time, with the gray trajectories forming knotted spiderwebs beneath it all. Some areas had a lot of bright collisions, some had very few, some had more particles, some less. Some had thick knots of gray webbing, and some areas had almost none. "What is that foamy gray stuff?" I asked. "More inflaton stuff?" She replied, "For this epoch, I'm letting you see dark matter, which has emerged as the universe has continued to shatter into different fields. I'm pausing it here because this is the beginning of the Electroweak epoch. And this will conclude part 1 of the most important science lesson ever. Your body is now in this new phase of the universe, the observable universe, but your feet are still in the inflation epoch." I replied, "I don't understand how any of that is possible. First of all, how can my head and feet be in 2 different times at once? And how can the universe suddenly go from ice cold to back to insanely hot again? My body felt like it was on fire, while my feet felt frostbitten." She said, "From your human perspective, your head and feet are always in different times, even back on Earth. If you stub your toe, it takes several nanoseconds for the pain signal to arrive at your brain. Similarly, your toe is several light nanoseconds from your eye. So you always see and feel your toe as it was a few nanoseconds ago, unless you stick it right up in your face. So the toe you see and feel and can observe scientifically always exists in the past, at least as far as your observing head is concerned. How long is a light nanosecond? Much shorter than a light year. It's about 12 inches, a foot. It's how far light travels in a billionth of a second, which is a nanosecond. Everything that you ever see, you're seeing in the past, from either a tiny bit in the past, like if you look at your nose, to all the way back to the Big Bang, like when you look out to the edge of the universe. Even what your eyeballs see takes a little time to register in your brain." My face felt like it was starting to blister, and my feet were now completely numb. "Can we move it forward so I'm not in so much pain?" "Oh, sorry about that," she said. "Here, take a seat for a moment." Sophia moved time forward just enough that the fireball universe was now big enough for me to sit cross-legged in again with my head in the middle. The heat felt good on my feet, and my head felt a little cooler with the extra expansion of the universe. Of course, my head would have been instantly vaporized if I were experiencing it in my real body, because the universe was still... How hot is it now? 10 to the 27 degrees, or 100 million trillion times hotter than the center of the sun. And why did you pause it here? Because I want to show you the difference between the observable universe and the entire universe, or the unobservable universe. Okay, good, because I'm still not clear on why part of it would be unobservable. You saw the entire universe from the beginning of the Big Bang until the beginning of inflation, when both you and the entire universe were much smaller than a proton. Now you're back to your normal size, and the observable universe is almost 2 meters or 6 feet wide, and it's hot, and it has moved into the Electroweak epoch. But the rest of the universe is forever stuck in the first 3 epochs from your perspective. You will never see the vast, cold, dark inflation universe ever again, not even with the most powerful telescope. Why not? Because inflation has pushed that part of the universe so far beyond us that even though the expansion of the universe will be sub-light speed from now on, any light or gravity waves that are beyond this sphere will never reach us, even at the speed of light. This is the difference between the observable universe and the much larger unobservable universe. Just like the Earth is much bigger than what you can see when you go outside for a walk, because the horizon blocks everything beyond it from view, so the point at which light itself recedes from us too fast to ever reach us is a horizon that blocks out the huge part of the universe that lies beyond it. So I want you to get used to this new, smaller universe, because that's all the universe you're ever going to see. Right now, it's a couple meters wide. 13.8 billion years from now, when you get back home, it will be about 93 billion light years wide. I asked, wait, if it's expanding at or less than the speed of light, shouldn't it be at most double 13.8 billion light years wide, which would be 27.6 billion light years wide? No, because the stretching of space happens everywhere, so it is cumulative. It barely seems to be expanding at all at the center where the observer is, but it becomes exponentially greater the farther you look out. That's why it's always going to seem like the universe is expanding faster than light out at the edges. I asked, and how will the edge of this little observable universe ever become visible to us if its light has to travel 46.5 billion light years in only 13.8 billion years? Oh, wait, I get it. The light waves themselves get stretched out as they travel along. That's right, Sophia affirmed. Their history gets stretched out along with space from the observer's perspective. The visible light from the edge of the orb that you're seeing right now, that light is the waves. The expansion will stretch the journey of those light waves reaching your eye, but as long as they set out on their journey 13.8 billion years ago and weren't sucked out beyond the observable horizon by inflation, everything in this observable universe will still be observable in the 21st century, despite the expansion of space stretching everything out. I replied, space and time are very stretchy. Space and time are indeed stretchy and bendy and squishy and curvy. The sooner you get used to that idea, the easier cosmology and astronomy will be. I said, and the observer is always in the thick of it. Yes, she replied, always, always in the middle, because that's how looking works. The farther away you look, the farther back in time you see, no matter if you look down, up, front, back, or side to side. The important lesson right now is that you understand what the observable universe is. I think I do. It's the universe that is visible to an observer because it is all its light is within the horizon of all the light had time to reach us. And if the light doesn't ever have time to reach us, even though it's going light speed, it's outside the observable horizon, and so we'll never see it, and so it will never be observable. Not bad, she said. Now that you understand, and now that you know you'll never see the universe outside this little orb again, I'm going to stop saying observable and unobservable universe. From now on, this little orb is the universe, because it's the only universe humans will ever see. So right now, the universe is only a couple meters wide. Wait, I said, first let me say goodbye to the stuff beyond the horizon. I reached out and touched the edge of the observable universe. I pushed hard, and my fingers went through the horizon back into the inflation epoch. It felt like the tips of my fingers were stretching out millions of miles into cold, empty space. Whoa, weird. I pulled my hand back in. Okay, I'm feeling claustrophobic. I'm ready to move on. But first, everything in the universe I knew back home, the 93 billion light-year universe, is all right here with us in this little 2-meter wide orb? Yep, she said. The few trillion galaxies in your 21st century universe are all crushed into this extremely dense little ball we're in. And the trillions of galaxies in the part of the universe you'll never see again are nothing but quantum fluctuations in the inflation epoch, and they'll stay that way for all eternity from Earth's perspective. And with that, she made the dense particle zoo reappear, and the orb began to expand again. This time with the speed of a true explosion, even though the Big Bang was not an explosion, but just the expansion of space. She explained, we will now watch in slow motion the rest of the first 100 billionth of a second of the universe's history. I once again saw the furious storm of particles buzz about my head. She continued, the Planck, grand unification, and inflation epochs all together only lasted a trillionth of a trillionth of a trillionth of a second. So this new epoch you're seeing, the Electroweak epoch, lasted a trillion times longer than all of them combined. During this time, the universe grew from about the size of a human to a little less than the distance between the Earth and the Sun. I felt relieved that I could now stretch out and look around, and I was glad that we were now moving through time at a good clip. Well, I guess a trillionth of a second isn't a good clip, but compared to inflation and earlier, we were really moving along now. I asked, so what happened that made the universe hot again when it got so cold at the end of inflation? She explained, we went through another phase transition. Or perhaps more accurately, we saw the end of the phase transition that tore the strong nuclear force away from the electroweak force. At the transition from the grand unification epoch to the inflationary epoch, all the energy of the universe got dumped into the inflaton field. Then, at the transition from the inflationary epoch to the electroweak epoch, all that energy got dumped back into all the other fields, resulting in the inconceivably dense thermal bath of particles surrounding you now. In other words, all those inflaton particles you saw come into existence when they were ripped apart from their virtual partners decayed into the zoo of particles you see now. Decay? Particle decay means that a particle changes from a type of less stable particle to one or more different particles that are more stable, with stability having a lot to do with the temperature and available energies. Now, here is the finale of part 1 of the most important science lesson ever. Okay, I'm ready. Do you see how some parts of this fog of particles seem a little thicker than the other parts? She asked. This, of course, isn't something a normal person would be able to see. Sophia was again giving me microvision. Yes, I replied. It's like lumpy. Thick lumps here, thin lumps there, and lumps within lumps, and lumps within those lumps. It's like how I was seeing space get thick or thin when positive or negative inflatons were becoming real. Exactly, she said. That's what happened. The positive inflatons made the energy of space a tiny bit denser, and the negative inflatons made the energy of space a tiny bit thinner, and this made space lumpy. And the earliest lumps to form got huge because of inflation, and the very last lumps to form before the phase transition were extremely tiny. And there were lumps of every conceivable size between the biggest and smallest lumps because throughout inflation, inflatons kept emerging and kept getting torn apart and kept making permanent dimples or bumps in space throughout the whole epoch of inflation. Then, when the phase transition happened, all the energy of expanding space turned into the energy of all these new particles, which is why the universe reheated to 10 to the 27 degrees, as if inflation had never happened. This event is called cosmic reheating, and cosmologists call everything that occurred after inflation the hot Big Bang. Not that the universe before inflation wasn't hot, but we simply don't know for sure what happened before or even during inflation because inflation erased that universe by pushing it beyond our horizon. Now, in those slightly thicker parts of space, the slightly greater energy density of the inflaton field decayed into slightly more of these new thermal bath particles. To be more specific, the end of inflation didn't happen everywhere at exactly the same time. Remember how we said that the fluctuations in the inflaton field changed the value of the field so that the fluctuations corresponded to, for example, 100,001 or 99,999? Yes, I said, but why those numbers? She said, I just made them up for example's sake. We don't really know the natural value of the inflaton field. We just know that at a certain critical value, inflation ended. So let's pretend that at the beginning of inflation, the normal value was 100,000, and that during inflation, it decreased everywhere in the universe at the same rate. And let's say that +1 and -1 fluctuations were superimposed on the field so that some parts had a value at the beginning of 100,001 and others 99,999. And finally, let's say that 30,000 was the critical value at which inflation would end, causing the inflaton particles to decay into all the dozens of kinds of particles we see now. When the virtual inflatons were torn apart and became real particles, the value of the field permanently became +1 in some places and -1 in others. What this +1, -1 imbalance means is that the -1 places reached the critical value of 30,000 slightly sooner than the +1 places. When those negative regions converted all their inflaton particles into this hot plasma we're in, the normal sublight speed expansion of space continued, which diluted those regions and made them slightly cooler and thinner. When the last of the positive regions stopped inflating, their inflatons decayed at the same density and temperature as the negative spots when they exited. But those negative spots had already been diluted just a tiny bit because inflation ended earlier for them. This is the reason for the uneven density and temperature in the universe. The negative fluctuations exited inflation sooner and resulted in slightly cooler and thinner regions, while the positive fluctuations exited inflation last, resulting in slightly denser, warmer regions. These are called the primordial density perturbations. A perturbation is a sort of disruption in something that's sort of otherwise even. I asked, is this why I saw the ball of fire form around my head unevenly? It was fast but kind of spotty. Yep, that's exactly right. And those first spots to form got diluted by the continuing expansion while the last spots were forming. That's why you now see thicker and thinner patches of particles all around you, and they're all due to virtual inflatons being torn apart and turning into real negative or positive inflatons and then decaying into all these new particles. Now let's fly around and take a tour. Sophia returned to her angelic form and took me by the hand. The universe was now plenty big enough for us to fly around in. She said, you'll see that as we fly through the particle fog, as we expect, some parts are a tiny bit thicker and hotter, and other parts are a tiny bit thinner and cooler due to the primordial density perturbations. If we make ourselves really big as the Earth, we still see this lumpiness. If we make ourselves really tiny, as small as an ant, we still see thick clumps mixed among thinner clumps. We see this lumpiness at every scale because young quantum fluctuations were happening on top of ever-expanding large old quantum fluctuations. This imperfection, this inhomogeneity, these perturbations in the density of the universe are all due to those random quantum fluctuations in the empty inflaton field. And these random density perturbations, these lumps of slightly thinner or thicker clumps of particles, were forever frozen in place when inflation ended. And this seemingly ugly random imperfection that permeated the universe and that completely baffled us angels is the most important science lesson ever. I don't get it, I said. You will when we see how these variations in density cause the universe to evolve. Okay, I said, I trust you. Good. I must say you're a good student. Thanks. What makes a good student? Good students are patient with themselves and their teachers because they realize how difficult learning is and how great the effort required, which can sometimes be overwhelming, and this can lead to frustration. Anyone can understand this stuff with time. Some learn quickly, some slowly, but with patience and perseverance, anyone can do it. That's good to know, I said. We are approaching the end of the Electroweak epoch, she said. The universe right now is much larger, but it could still fit snugly between the Earth and the Sun. So it's still incomprehensibly dense. I guess I should tell you why it's called the Electroweak epoch before we move on. I interrupted. You said that the strong nuclear force started to split off from the electroweak force, and that started inflation. Yes, she said. That's why this brief part of the history of the universe is called the Electroweak epoch. It's the era in which the temperatures were still so high that electromagnetism and the weak nuclear force acted as one force. That's why the universe is in reality still pitch black, even though it's a hot fireball. There is no electromagnetic field to carry photons, which is what light is. Instead, the electromagnetic field is welded to one of the weak nuclear force fields to make the hypercharge field. Other than these weird electroweak fields, all the fields and particles known in the 21st century are here in this dense fog, and we are finally on solid ground scientifically, because humans can recreate the lower end of the extreme temperatures of the Electroweak epoch on Earth using particle colliders. Like the Large Hadron Collider? Exactly. So humans can not only look back to the beginning of the universe through telescopes, but they can also peer into what the first trillionth of a second was like by recreating the conditions that prevailed during the Electroweak epoch. Everything before the first trillionth of a second becomes more and more speculative the farther back we try to go. I asked, do we know for certain that the Planck grand unification and inflation epochs happened? She said no, although inflation is looking solid right now. I asked, but then how can it be the most important science lesson ever if we're not sure? She said, it's the primordial density perturbations that are the most important science lesson ever. At least, they're the most important in terms of the story of the universe's evolution. And even if we find out that inflation and random inflaton fluctuations didn't cause these density perturbations, the density perturbations nevertheless still exist. We can see them from Earth when we aim our most powerful telescopes at the edge of the universe. So if inflation didn't really happen, then we must explain the density perturbations another way. Perhaps they were built in from the very beginning. In any case, they're real, and you'll see soon why these imperfections in density explain the whole story of the universe. One more thing I should mention is that all the particles you see swarming about are still massless, so they're all jostling around at the speed of light. That's about to change. As we approach the final phase transition, I'm going to give you back your normal vision. Everything went black again. I was ready for photons.